Hi, in this video I'm going to cover some advanced techniques of recurrent neural networks and the use of convolutional 1D layers for accelerating recurrent neural networks. These type of layers are good for problems whose data depends on the sequence order and also for natural language processing. The material that I'm covering here corresponds to the last part of chapter 6 of Francois Chollet Deep Learning with Python book. In the first example, we're gonna make a model that predicts the day's temperature, and it's gonna be trained with weather data coming from this link. In here, we download a big comma-separated value file. I place it into this folder, and basically the first line is gonna be the categories, and the other lines, which are a bunch of them, if actually 420,000 lines, is a bunch of data. Is basically the numbers corresponding to each column. So you have the first is a date, which we ignore. We capture the sequence in the relative order of the data, so we don't need the date, so we take it away in the training. And then you have pressure, temperature in Kelvin, and all the weather information that, although it's not predicted, we're going to break this one only, but this one is used as features to be able to detect this, because all of pressure affects temperature, so that's important to include in the neural network. Okay, so I'm not going to give a detail on how to do the data pre-processing. It's basically parsing this file and put it into a tensor, a contiguous tensor that a neural network is expecting. And also I'm not going to run the scripts because the neural networks take a lot of time, but I'm going to show all the results. There was one network, the one with stack layers, that took almost an hour or more to train, so it's not practical to run it live. Okay, so the first part is pre-processing, basically parsing the lines and splitting them by comma. And you can see that this is a bunch of data. You're gonna have 15 headers. We take it once, so there's a total of 14 columns of data like this, and we place them into this tensor right here. Okay, so you can see that the data is pretty periodic over the full range, and but if we get a smaller sample, you can see it's a little bit more chaotic. Okay, but then also we're going to normalize the data. NumPy provides some the mean and standard method to facilitate that. Neural networks are friendly towards normalized data, so that's good to do. We only do it in the validation data, in the training data. The validation doesn't need it, I suppose. Okay, so since this is a bunch of data, these are the 14 categories and the sample dimension. Since it's a bunch of data, it's convenient to have to use a generator to basically sample it liter by liter. Okay, the generator is a Python construct that facilitates, at least in this case, it helps getting data chunks by chunks, and all of these parameters are going to determine the size of the chunk. Okay, so we're gonna the key of the generator. The generator is a regular function, but the key is yield. Yield is like a return. In this case, we're returning a chunk of the weather data, and this is the expected temperature, the one that is used for the loss function to train the neural network, and this is the input of the neural network. So we're gonna create some chunks. We do some calculations based on this and return a chunk. So the next time that after returning yield, the next time you call it, when you ask for the next value, it's gonna go. It's gonna continue execution, and this can easily be seen in this example. So for example, I have a generator. When I create the generator, when I do this, this is gonna be a generator object. So it's like a class. And when I hit next, then it's gonna run it, and then it's gonna assign value n equal to 1, return 1, so we get 1. That's one. It's like a return. But the next time you call it, it's gonna continue into this place. So it's like a freezing in the place where you call yield, and then continue until there's no more execution. Okay, so this behaves very similar to what MATLAB Datastores do. There's a reference of that in this video. I found MATLAB Datastores a little bit more easier to understand, more convenient, because basically it's like an object, and you basically provide a callback, and the callback iterates through all the data, and you can augment the data, do normalization, over transformation, batches, etc. And also the deep learning objects in MATLAB are ready to communicate with this data store. They take them as an input for training, and they call the equivalent of give me the next data, give me next data, and the same happens here in Keras. For the models are ready to talk with these generators, and they take them as input for training the neural network, and they call the next to get the data. Okay, so here we are creating the 3 generators for training, validation, and testing. Okay, so yeah, when you create one, you get a generator object, and when you call next on it, you get the tuple of the sample and target. And you can see that the shape of the sample is like it has splitted the sample dimension in the batch, the dimension of the batch, and the dimension of the sequence order. And then you have the 14 dimensions of the weather columns data. And then you have the output, which is a temperature for prediction, the target. Yeah. Okay, now we're gonna determine the steps for validation and the steps for testing. And I divided by 100 because there were too many. And without doing this, the training never ended. So maybe that's why the values are a little bit different from what you see in the book. But at least it is clear the relative difference shows what each variety of networks are intended to do. Okay, so first, one common strategy that the authors suggest is that when you're designing a neural network, start with a naive baseline method that doesn't even have to use deep learning. So in this case, what we're gonna do to predict is taking the predicted value is gonna be the last in the sequence. So that's gonna be our predictor. It's very dumb, but now we're gonna compute the mean absolute error by getting the loss function against the target, the expected value, the training data, and then just collect all the mean absolute error. At the end, we take the mean of all of it. So the mean absolute error of this naive computation is 0.29. Okay, so the mean absolute error of our neural network has to be below that. If you multiply that by the standard deviation, then you get the Celsius, which is I guess the error, more or less 2.57 Celsius. Okay, so now let's try our first naive neural network model, which is using fully connected layers, and we're gonna flatten the 2 dimensions that we get in here. These two, everything, we're gonna flatten everything, and then have a dense, and then have a dense layer that returns one single output. There's no activation at the end because we're returning contiguous data, which is the temperature. And so this is our model. So let's just run it with 500 steps per epoch, 20 epochs. I think this number is too much. Usually they give the best value between the third one and the 10th epoch. Okay, so we're passing the validation generator, the generator that we created, and this is training generator that we created up here, in here. Okay, so let's train it and see what happens, and we can see that the validation loss gets to a minimum in somewhere in here in the fourth one, 0.30, and that is 0.1 on a almost 0.1 or a little bit more than 0.1 above the naive method that doesn't use neural network. So that's pretty bad, because the naive method that we did here does better than a neural network. And it is expected because the data is a sequential data that depends on time, and we are using a fully connected layer which doesn't capture time. For that, we have recurrent neural networks like GRUs or LSTM that have a state in order to be sensitive to the order of the data. Okay, so we're gonna go not gonna go details on this. You can watch it on your own how to plot things. It is generalizing well, but the value is off. Okay, now let's try recurrent neural networks. We're gonna try GRUs. I'm gonna show first a diagram of it. So here's an illustration from the deep learning book from Goodfellow, which is also on the references, and the paragraph above is from the Francois Chollet book. He mentions that Chong is the inventor of this, and that GRUs, a gated recurrent unit, is a streamlined version of LSTM. Let's take a look at LSTM. This you can take a look at the previous video that talks more about this. So this should be more easier to compute, but less expressive. And he mentions that in neural networks, deep learning usually see that trade-off between expressiveness and precision and computational capacity. And we're gonna see it also later when we use convolution layers combined with recurrent networks, which speed up the training but are not as precise. Okay, but speeding up the training sometimes makes a difference between having something that is practical and something that is impractical. Okay, so let's train for it. We're going to use the same validation generator, same configuration. We just change the GRU using the tensor weather data shape as the input. Very simple. And it reaches minimum of 0.26. So this is 0.03 better. This is better than the naive implementation. So we already improved it. So this is good. We have an improvement over the baseline. Okay, but let's see how good it regularizes the gap between the validation and the training is like 0.8. So it's overfitting, clearly overfitting. So we have to use regularization techniques, and one of them is dropout. The author mentions that Yarin Gal found that using the same dropout throughout time steps is more effective than just randomly doing dropouts in each time step. And also he found out that GRUs, which is recurrent and have a state, you can apply both. You should apply the dropout both in the input and also in the state. Okay, so that's the only difference. We specify those two parameters, and you can see more about it in the documentation in here. So you have the dropout, recurrent dropout. So yeah, it's for the state. Okay, so now let's train it exactly the same way. And we see that a minimum is 0.26, which is good. We were not looking for improving the precision, but we were looking for improving the generalization. So let's see how it generalizes. So the minimum gap, the maximum gap is at the end. So it should be 0.8, almost the same, but I guess yeah, I guess that if you play around more with the dropout, the gap could be reduced. That's the idea. Maybe it's the amount of validation data that I'm using less validation data to be able to run these examples. Maybe if I were using the whole data, the gap would be reduced better. Okay. In theory, if you were able to reduce the gap and are able to generalize better, the next step to increase precision of the model is to increase the complexity of the model, and one way of doing that is incrementing the number of layers or stacking recurrent layers. And he mentions that that probably is not mentioned here. Yeah, the Google Translate algorithm has 7 layers. Okay, so training this network in particular took maybe more than an hour for me. So I went to it, I went to bath, I went to do a lot of stuff. I even went out of the house and came back, and it was still training. So yeah, it was painful. So I suppose that maybe Google training those 7 layers for doing that Google Translate might take longer. Okay, so it's the same. But notice that in the previous video I talked more about these return sequences. So yeah, I'm gonna show briefly the difference. If the default value of this is false, so when it is false, you're gonna get a summary. You're gonna get something like this. So you have an input sequence and the output is a scalar. But if you specify true for that parameter, you're gonna get something like this. You keep the sequence, so you have an input sequence and output sequence. Okay. So notice that the first layer has it, but the second doesn't, because you are only interested in getting a scalar temperature prediction, but you want to keep the sequence information in order to fit the second one. Okay, so that's it. Everything else is the same, and notice that we have dropout for both of them in both input and state. And let's train it exactly with the same training generator, validation generator, same configuration. But since we have more parameters, then the number of epochs was increased. But that didn't really help a lot, because in the sixth one we got the maximum value, but I guess it's to measure the generalization capability. So it reached 0.26, so it didn't help. Adding complexity didn't help, so we should not do it in this case. Just adding training more computation. So at the end of this is terrible. Even generalization is not better. We have a bigger gap. Okay, so that was not a good idea. Okay, another strategy that he suggests is using bidirectional layers, which is basically it's like a Swiss Army knife for deep learning for natural language processing. So the idea is basically that that by getting the reverse information, you can detect patterns that you cannot detect in the forward direction. So let's show an image about bidirectional layers. Okay, so this is from Goodfellow. So he shows it like this. It's basically like a recurrent network that the state depends on the previous state and the input, but also this one depends on the previous state and the output just go in the opposite direction. And this image is from the Francois Chollet book. It shows how Keras should be doing it. Keras basically the bidirectional layer is a wrapper to a recurrent neural network, which could be GRU or LSTM, and one of the layers has a sequence in order, and the other one gets the sequence reversed. Okay, so in order to illustrate when this is important, it goes back to the IMDb example. You can find more details about this in the previous video about recurrent neural networks and the embeddings video as well. So in this example, there's a set of reviews for movies, and we want to predict if the movie is positive or not, and if the review is positive or not, and this is a boolean that we get in here, and here we get a set of paragraphs encoded. Okay, so in order to make it a tensor, it's going to apply padding, so puts a limit of 500 words. If you go beyond it, it's going to clip it. If you go below it, it's going to put 0, so you have a contiguous tensor. And okay, so we're gonna the point that he's trying to illustrate is that this problem is not dependent on sequence. It's sentiment analysis, and you can, it's basically you have to just detect all the words, and by the words you detect if it is positive or negative the review, and the order does not matter. So he wanted to show it here. So he applies the same embedding that he did before, and we using an LSTM, but he's gonna reverse the data in here. And after reversing it, he's gonna feed it. I think it's the same network that he applied in here. This is from the previous video. So using exactly the same network. The only difference is that we are reversing the data. And when we train it, we get 0.88 maximum. And let me see how much he got. The previous one, 0.89 the maximum. So it's almost the same. So it shows that reversing the data did not affect. And so then he tries to use bidirectional layer with LSTM, exactly the same thing but bidirectional, and then train it again, and you get a 0.86 maximum. 0.87 actually, it generalizes better for some reason. Let me see the maximum. Okay, so it's 0.11 the difference between training accuracy and validation accuracy. Let me see here. It's 0.13, so it did generalize better. It looks like, let me see the validation accuracy. You can see a gap in here. It looks a little better, but it doesn't make much difference really. That's the point that he's trying to show. So now he's gonna apply it to the weather information that is chronological and should be improvised. Okay, so we're gonna use a bidirectional one layer GRU with the weather data. Okay, so let's train it with the generator, validation generator, and train generator that contains the weather data, and it goes down to 0.26, which is the best that we have obtained so far. Okay, but doesn't look that it's generalizing well. Yeah, actually it's pretty bad. The generalization is pretty bad, so this is not the best option. You can see the huge gap in here. Okay, so a few tips that the author mentioned is that in order to make the network better, you can adjust the recurrent layer features, adjust the learning rate. This is a hyperparameter that is one of the most important to take into consideration to calibrate it well. Try using LSTM instead of GRUs. As mentioned before, LSTM are more expressive but takes more time to train. Also, you can use bigger densely connected layers at the end, maybe adding more features to them, and eventually apply check the test data set to verify that it's predicting well. As mentioned before, in general, you want to try with a non-deep learning baseline, like the naive implementation that we have. Start with a simple model first, then use recurrent neural networks if the problem depends on the sequence, otherwise maybe convolution if it is related to contiguous multidimensional tensors, and also you can consider dense connected layers and other layers. Okay, then if your network does not generalize well, if it overfits, then apply regularization strategies like dropout. And if you're generalizing well but not predicting well enough, then you can consider augmenting the complexity of the model, maybe by stacking, by adding more layers to your model. And then you can keep going, applying more regularization if needed. Okay, now finally we're going to talk about the 1D convolutional layers. This one of the main advantage that the author is trying to show here is that the convolutional layers compared to the recurrent layers are cheaper to compute. So if you have a long sequence, you can use it before the recurrent layer to reduce the size of the sequence, and this is illustrated in here. Let me show the image. So you can have a long sequence, feed it to the convolutional network, and then have a shorter sequence, and then apply the recurrent network. So convolution in one dimension is similar to the 2D convolution that you see for object detection in images. You can see a reference for that in this video, which comes from the chapter 5 of the Deep Learning with Python book. Okay, so let's first try the convolution on its own. Okay, if we're gonna try it with IMDb data, again, it's gonna clip it, create the tensor, and we're gonna train it. We need the embedding because we have encoded vectors for words and encoded words for words, and then we're gonna have the output number of features for the vector. And since we are dealing with a linear 1D convolution, then we can have more. The size looks larger because when you have a 2D convolution, you have, for example, a 3x3 matrix, which is a total of 9 elements. But since this is sequential, you can have a higher number, which actually is less numbers than the 3x3 in the two-dimensional case. Okay, so again, apply max pooling, and then finally apply global max pooling, which I didn't saw this in for the image convolution, and finally advanced to do the classification of the positive or negative review of the movie. Okay, so let's see how this does. Let's train it, and we can see that it did pretty well. It generalized. It improved at the end. This is rare that you get the maximum near the end. So it looks at least not generalizing bad. But 0.87 is almost as good as the best that we got in here, which is 0.88. But the difference is that this is using an LSTM, which is harder to train, and this one is using pure convolution. So that's a big difference. There's no recurrent neural networks in here, so the training should be way faster. And I checked that this was faster than the previous recurrent networks above. So this is preferable. Okay, if you are constrained in the training time. Okay, so now let's try it with the weather. The weather is a time-dependent sequence, so we have. So again, we use convolution. 1D convolution is very similar, but notice that we don't have recurrent layers, and this has sequential data. So let's see what happens. Same training, we use the training generator, validation generator, and we have a horrible 0.45 with a very bad gap. So yeah, that's expected because this is a sequential problem. So we have to combine the 1D convolution with the recurrent layers. So again, we're getting the generators. I don't know why we're getting it again. I already defined them. But anyway. Okay. Okay, so now we put a GRU at the end of the second convolution with the dropout for regularization for both state and input, and we replace the max pooling, the global max pooling, by the GRU. That's what we did. The rest is basically the same. Okay, so we train it and we get a minimum of 0.28. 0.28 is the minimum, which is not bad, but the goal here was not improve the precision but reduce the training time, and I understand that we achieved that goal. Okay, so that's it. Thank you very much for your attention.